Swayam Prabha. Digital India. Educated India.
Followed by classical machine learning techniques, under which you have algorithms like perceptron, logistic regression, support vector machine, graphical models like hidden Markov model, maximum entropy Markov model, conditional random field, and so on. So we would like to take up maximum entropy Markov model and conditional random field in one of the classes to show how they are used in solving NLP problems. And recall at this stage that a large number of NLP problems are sequence labeling kind, because language is expressed in terms of sentences or sequence of words, and many things are done on sequences of words. And finally, on the technique axis, so the last column is on deep learning, where you have dense feed-forward network with backpropagation and softmax. This is the classical multi-layer neural network. And then we have recurrent neural networks, again a classical neural network, because this introduced feedback into the framework. In the feed-forward network, which is dense feed-forward network, there is no concept of feedback coming from one layer into another. And I think a slightly different kind of framework is convolutional neural network, which does pooling on the input. Okay, and these are the top level categories of deep learning techniques: dense feed forward with backpropagation softmax, recurrent neural networks (LSTM), convolutional neural networks. So these are the three major ideas, and there are variations on these combinations of one with another and so on. Similarly, on the classical machine learning front, we have support vector machine, logistic regression, decision tree, graphical models. These are the major ideas and techniques. Under rule-based systems, of course, we have rules with strengths of rules given in terms of probability, certainty factor, and so on. And on the problem axis, we have morphology, part-of-speech tagging, chunking, parsing, name recognition, co-reference resolution, words and disambiguation and semantic role labeling, multi-word extraction, sentiment and emotion, question answering, machine translation, of course, that falls below the screen. So these are major tasks with respect to language processing and major approaches with respect to technique. So this is task versus technique matrix. And if you look at different NLP courses all over the world, you see a kind of spectrum. There are courses which are technique heavy, in the sense that they emphasize the techniques, bring out the nitty-gritties of the techniques. And the other end of the spectrum would be understanding the problem thoroughly through linguistics, cognitive science, philosophy, world knowledge, even physics, and so on. So depending on who teaches the course and where it is offered, depending on the culture of the department, institution, the courses fall in the spectrum of task heavy to technique heavy. Okay, we would like to strike a good balance of task understanding and technique understanding in the course. So right now we are spending time on the pause row and graphical model column. Okay, so we are operating with part-of-speech tagging as task, and one of the graphical models, very well-known graphical model, hidden Markov model, applied to part-of-speech tagging. Now the point is that in these courses, which are done in academic institutes of high repute, we always aim to bring out generalizations and unifications whereby the students are empowered to take up new problems and new techniques. So what I mean by this is that once you have understood hidden Markov model and part of speech tagging, it will not be difficult for us to appreciate conditional random field applied to named entity recognition. Okay, because this task and problem combination, this task technique combination has elements of generality which are applicable to other task technique combinations. Okay, so it is worthwhile spending some time on part of speech tagging and hidden Markov model, because you can translate this understanding to other task technique combination. So let's proceed, and would like to leave enough time for question answering and doubt clearing. Part of speech tagging was defined to be picking up a tag from a tag repository. We discussed pen pause tag repository. And let me repeat this very important exercise for you, where you give tags to sentences presented to you and construct sentences where these tags are applicable. For example, with JJ, construct a sentence where JJ can be inserted. So I saw the blue sky. Here blue will get JJ. And I will get the tag of PRP, personal pronoun. So we spent some time discussing pen pause tag set, which has remained for English language part of speech tagging and has been an inspiration for pause tag set of many different languages. In particular, the BIS tag set, which we designed along with other NLP groups in the country for Indian languages. We took an example of part of speech tagged corpus, where the tags are given after this forward slant. Sometimes they're given with underscore. So how forward slant WRB, WRB is a tag, but it could also be written as how underscore WRB. And WRB, you remember, is a WH adverb. How is an adverb because it depicts the manner of an action. So it is an adverb of manner. So this is the way the corpus is pause tagged, and we trained a machine learning model with this training corpus. Let me re-emphasize that this task of inserting tags on raw text is called annotation, and this is a sophisticated task requiring language expertise and understanding of the context. Mathematics of pause tagging led us to transition probability and lexical probability, which is nothing but observation probability, and we could for bigram situation where the transition probability is only dependent on the previous state, then you can draw a finite state machine with probability on a piece of plain paper on the two-dimensional plane, and this finite state automaton with probability is called the hidden Markov model. What is hidden here are the states, and it is the states we are interested in. We also saw that these observation probabilities can be eliminated by multiplying those probabilities with the state transition. Okay, so n to v and n giving out people, if you multiply the probability of n2 people with n2v probability, then you can eliminate these observations, okay, and absorb everything in the form of an arc on which the label is people and n going to v. Okay, so this becomes your familiar finite state automaton with state to state transition with levels on the arcs. Only thing is that there is a probability value associated with each arc. Okay, and that probability value is the weight of this connection. Now the problem reduces to finding the best path from the start state, which is hat, to the end state, which is dot. And the best path means the highest probability path, which is nothing but the path with the greatest weight. And since we can multiply the probabilities on the path, we are interested in finding that path which has the highest probability, highest product of the constituent probabilities. So now you can appreciate what I said when we mentioned that task technique combination is educative, because you can apply many of the ideas to a new situation. So given any such graph with start state and end state, computer scientists are extremely familiar with the method of finding the best possible path, quote unquote best. Okay, here best possible path is that path which has the highest product of probabilities. So now if you go to conditional random field maximum entropy Markov model, the only thing that changes is the method of getting probability values from state to state on an observation. That is all. And the same method of decoding, the Viterbi decoding, applies. So we'd like to make our understanding clear on Viterbi decoding and understand why Viterbi decoding is needed. So we were discussing hidden Markov model because that is the generalization of this kind of probabilistic finite state automaton. Hidden Markov model is formalized as a 5-tuple of states, observations, transition probability table, observation probability table, and the initial probabilities. The observations are often put in a sequence, and we were interested in the state sequence corresponding to that observation sequence. So we took as an example the ARN task. We have to find out the best possible state sequence given the observation sequence, which is the color of the balls drawn. So we are given transition probability table, lexical probability table, or observation probability table, and that is expressed in the two-dimensional plane by this kind of automaton. But we could absorb the observation probabilities into a kind of combined transition and observation probability, and could draw this diagram in a different manner on the two-dimensional plane. Then we were interested in probability of S given O, and we had to apply the Bayes theorem and cast the problem as probability of state into probability of observation given the state. And from that, we came to a very useful expression, which is the probability of state into probability of observation given state is nothing but the product of probabilities of transiting from one state to another on an observation. Okay, so when we take this RR, GG, BR, GR observation, then the states are S1, S2 up to S8 corresponding to these 8 observations, and we have a fictitious state S0 and S9, which are sequence beginner and sequence finisher. And from S0 you go to the state S1, and from S1 to S2 on different observations. Okay, so you can take the product of these probabilities from state to state on a particular observation, and this is nothing but the conditional probability of observation given the state into next state given the current state. You can take the product of these two probabilities. So then we are on a strong footing with respect to the theory of the hidden Markov model, and we apply it to our part of speech tagging situation. So we have the sentence brown foxes jumped over the fence. The sentence beginner is hat, sentence finisher is dot. And the tags possible are brown has adjective and noun possibility, foxes are plural noun and third person singular number present tense possibility, jumped is past tense and adjective possibility, over is noun, preposition, adjective and adverb possibility, the is dt, determiner, fence has noun and verb possibility. So from the first state, I have two possible states, NN and JJ. From NN, I can go to NNS VBS. From JJ, NNS VBS. So this way, from every state, I can write down all possible children. And this tree, you can see, has an exponential number of paths from root to leaf, exponential in the length of the input, length of the sentence. Okay, and remember we are interested in that particular tag sequence whose product of probabilities on the constituent arcs is the maximum. So we are interested in quote unquote the best possible path going from hat to dot, and we have to pick one of the exponential number of paths. Okay, so if each word can have t tags, then there are t to the power l leaves. T to the power l leaves. L is the length of the sentence, and then you have to find out of this t to the power l the best possible path sequence. The path sequences are shown in the form of a tree here. So that's a exponential situation and clearly undesirable, because you cannot spend exponential amount of time just at the level of part of speech tagging, because you have higher level tasks like machine translation, sentiment analysis, question answering, where the complexity is huge. So this particular stage of processing has to be efficient, which is at the lower level of NLP stack. So then the probability of a path, I'm taking the topmost path here, namely NN, NNS, VBD, NN, DT, NN. This the probability of this particular path is PT into PW given T, which is probability of hat, into probability of NN given hat, into probability of NNS given NN, into probability of VBD given NNS, and so on. These are all transition probabilities multiplied by probability of hat given hat, probability of brown given NN, probability of foxes given NNS, probability of jumped given VBD, and so on. Okay, so this is a fairly mechanical task to take this product of probabilities. Okay, and I can do it for each and every path exhaustively and pick the path which has the highest probability, but that would be an exponential task. So we come to a very clever idea due to Viterbi, and this is the Viterbi decoding. Okay, so Viterbi decoding is an efficient method of finding out the best possible path, where Markov independence assumption strongly influences the computation. And since in your assignment you are doing Viterbi decoding, your concept of the algorithm should become very clear through this implementation, and then you can apply the decoding idea in many different situations. So I illustrate Viterbi decoding with a very simple example. There are only two states, S1 and S2. S1 on A1 as observation comes back to S1 with probability 0.1. S1 comes back to S1 on A2, observation A2 with probability 0.2. S1 goes to S2 on observation A2 with this probability. S1 on A1 goes to A2 with probability 0.3. Okay, so there are only two states and only two observations, A1 and A2. And without worrying about many details, let us just note that each of this arc has some kind of weightage associated with. That weightage is linked to the probability of observation and transition. Okay, so right now let us focus our attention onto this weight, and we have made an observation of A1, A2 symbols, a sequence of A1 and A2s, and we would like to know what is the best possible state sequence for this. So the observation sequence is A1, A2, A1, A2. Okay, A1, A2, A1, A2. I should have written it here. So observation sequence is A1, A2, A1, A2. Now notice the search tree here, and mark very carefully the essential point of Viterbi algorithm as to why the technique comes down drastically from exponential complexity to linear time complexity. What is that trick or that assumption? Okay, so we start. We go to state number S1. We could have gone to S2 also, but the probability of going to S1 is 1.0. The probability of going to S2 is 0.0. So though S2 can be developed on every symbol, okay, there is just no point developing this, expanding this subtree, because it will get multiplied by 0.0, and the whole exercise will be futile. So start to S1 is fine, 1.0. From S1 I can go to S1 or S2. And what is the observation for me? A1. Okay, so let me note the probability of going from S1 to S2 on A1. This is 0.3, and S1 to S1 on observation A1 is 0.1. This is the case indeed, as I refer to the diagram given to me. S1 to S1 on A1 is 0.1, S1 to S2 on A1 is 0.3. So this is what is depicted here. Now from this S1, somebody verify you are seeing the Viterbi tree here. Developing the tree is the title on the slide.
Yes, sir. We are.
Yes, sir.
Yeah, some student please.
Yes, sir.
Okay.
Yes, sir.
Okay, great. So note also this epsilon observation right at the top. Epsilon is on no observation, I transit to S1 or S2. If I could have transited to S2 also, there would be a finite probability here. There would be a non-zero probability here. So S1 to S1, I have come, and S1 to S2. Now I look at S1, and I find out from S1 to S1 on symbol A2. Now the symbol is A2. Okay, observation has changed from A1 to A2. Next symbol in the sequence. So on A2, I go from S1 to S1 with 0.2 probability, and from S1 to S2 with 0.4 probability, observation being A2. And S2 to S1 0.3, S2 to S2 0.2 when the observation is A2. Okay, all these I read up from the finite state machine which is given to me. So now comes the most important point of the Viterbi algorithm. So notice that from start, I have come to a situation where there are 4 leaves, and all the 4 leaves are ending in either S1 or S2. Okay, because there are only 2 states, so they have to end either in S1 or S2. So there will be as many leaves as there are number of states. Okay, there will be as many leaves ending in a particular state as there are number of states. Okay, so the number of leaves here would be t squared, because this is the second level, and t is the number of states. Now find out all those paths which are ending in the same state. So there is one path, start S1, 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 start S1, S2, S1. Okay, these are the 2 paths, start S1, 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 and start S1, S2, S1. These are the 2 paths, both of them ending in S1. And now we ask, what is the accumulated probability? Accumulated probability for these 2 paths. The accumulated probability for the first leftmost S1 is 0.02. Why? 1 into 0.1 into 0.2. Okay, you have to just take the product of each probability on the arc. Okay, and this we are allowed to do because of the theory that we developed through Bayes theorem application, chain rule application, and Markov independence assumption. This 0.02. The path ending, the other path ending in S1 has the accumulated probability of 1 into 0.3 into 0.3, which is 0.09. So between these two paths, both of which are ending in S1, one of the paths has higher probability. Okay, so this path which is ending in S1, the second S1, has higher probability. 0.09 is more than 0.02. So now I record this, I note this. Similarly, I note the path probabilities of those paths ending in S2. So again, I have two paths ending in S2. So first path ending in S2 gives me probability of 0.04, 1 into 0.1 into 0.4. The other path gives me 1 into 0.3 into 0.2, which is 0.06. So now what I'll do is that I will only advance that subtree which has higher accumulated probability. So I could have advanced both the paths ending in S1. There are two paths ending in S1, but I will not do so. I will advance only that S1, that path ending in S1, where the probability value is higher. Similarly, I will advance only that state, okay, whose path probability is more than the other path probability with respect to state S2. Okay, so only one path ending in S1 and only one path ending in S2 will be advanced. What is the reason? The reason is that from these two paths ending in S1, the future will be identical. For both these two leaves ending in S1, the future is absolutely identical because both of them will see the remaining part of the sequence. There is no change with respect to observation and therefore no change with respect to the subtree that will develop below the two states S1 and S1. Okay, so and since your operation is taking product of probabilities, there is no way the lower value S1 will give you a higher product of probability. There is no way you can find a winner path from this loser S1. Okay, so between two paths, one of them is a loser, and there is no point advancing that state, that loser state, and developing the subtree further, because this cannot yield a higher probability path. The higher probability path, if at all, will come from the winner path at any level ending at a particular state. So this is the crux of the Viterbi algorithm. Okay, and you will algorithmize this, you will convert this into a technique. I'm sure there will be many questions on this Viterbi algorithm, but this is the main point.